Today we're diving into an idea that dramatically advanced deep learning, the transformer. The title of its foundational paper, "Attention is All You Need," was a bold claim in 2017, and the results quickly validated its premise.
I remember when we covered TCM 18304 about attention. We saw how it allowed models to weigh the importance of different parts of an input. But all you need sounds extreme.
Before the transformer, almost everything that handled sequences, like language, relied on RNNs or LSTMs, right? Or sometimes CNNs. What was the problem they were trying to solve?
Exactly. This paper opens by noting that the dominant models for tasks like machine translation were based on these recurrent or convolutional networks. They were effective, but had inherent limitations such as difficulty with long-range dependencies, sequential processing bottlenecks, and challenges with vanishing or exploding gradients over long sequences.
The transformer's big innovation, as the abstract states, was dispensing with recurrence and convolutions entirely. It proposed a new architecture based solely on attention mechanisms.
So it got rid of the sequential processing that RNNs are known for? No more hidden states passing information step by step through a sequence? That's a huge shift.
This sentence is key. We propose a new simple network architecture, the transformer, based solely on attention mechanisms. This was a paradigm shift for how models processed sequential data.
And simpler doesn't always mean less powerful. It seems like sometimes the simplest ideas are the most transformative, if you'll excuse the pun.
One of the huge practical advantages they immediately highlighted was that these models were more parallelizable and requiring significantly less time to train. This is crucial for large data sets.
I can see why that's a big deal. Training time is a major bottleneck in deep learning research. This would allow for much faster experimentation and scaling up models.
They demonstrated this on machine translation tasks, achieving superior in-quality results. For example, setting a new state-of-the-art on English to German, achieving 28.4 blue, a significant improvement, and English to French translation, 41.8 blue.
So, not only faster, but better too. That's the dream, isn't it? Better performance with fewer computational resources. It feels like a win-win.
But isn't it hard to model sequences without recurrence? How do you maintain the order of words if you're processing everything in parallel?
That's a great question, and it's a common initial confusion. The transformer handles word order not through sequential processing, but by injecting positional encodings. We'll get into that in the next scene.
This paper defined the architectural blueprint and introduced the core idea. Now, let's peel back the layers and intuitively understand how this attention is all you need mechanism actually works inside the transformer and addresses the order problem.
I'm ready. My mental model of sequence processing is still very RNN-centric, so I'm excited to see how this new picture comes together.
Building on the Attention is All You Need paper, this illustrated guide helps us visualize the transformer. It really breaks down the high-level components before diving into the details.
So let's start with the black box. What's the fundamental task the transformer's trying to do, especially in its original NLP context?
At its highest level for machine translation, it would take a sentence in one language and output its translation in another. It's an encoder-decoder model, like many prior sequence-to-sequence systems.
Okay, so it still has that encoder-decoder structure we're familiar with. The input goes into an encoder, and the decoder generates the output. That's a good starting point.
Popping open the black box, we see an encoding component, a decoding component, and connections between them. Each component is actually a stack of identical layers.
So it's not just one encoder and one decoder, but multiple stacked on top of each other. Is that like how deeper networks learn more complex features?
Within each encoder, the inputs first flow through a self-attention layer. This is the core mechanism. It's how the model builds context for each word in the input sequence.
Self-attention. So a word looks at other words in the same sentence to understand itself better? Not just the previous words, but all of them?
Consider the sentence, "The animal didn't cross the street because it was too tired." Self-attention helps resolve ambiguities. When the model is processing the word it, self-attention allows it to associate it with animal.
Ah, like a smart lookup. It's figuring out dependencies that are far apart in the sentence, which was a challenge for traditional RNNs unless they had very long memory.
You can think of it like an RNN's hidden state, which allows an RNN to incorporate its representation of previous words. But self-attention does this for all words simultaneously, not just sequentially.
So, if an RNN builds context iteratively, word by word, self-attention builds a richer context for each word by looking at every other word in one go. That's the parallelization benefit, right?
Precisely. The guide notes that the word in each position flows through its own path, and while there are dependencies between these paths in the self-attention layer, the feed-forward layers are independent.
So not entirely independent paths, but the bulk of the computation can happen in parallel. That's a crucial distinction. It's not a free-for-all, but a highly coordinated parallel process.
Now back to your excellent question about word order. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence. This is where positional encodings come in.
So the model doesn't inherently understand first word, second word, etc., because everything is processed at once. It needs a signal.
Exactly. We add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks. These are vectors that carry information about each token's position, allowing the model to distinguish between words at different places in a sentence, even if they're semantically identical.
So each word's embedding gets a unique address added to it. The attention mechanism then sees this combined signal, letting it consider both what a word means and where it is in the sequence. That fills a huge gap in my understanding.
With the positional encoding added, the model now has all the context it needs. This high-level view shows us the components and the core idea of self-attention. But how exactly does this looking at other words translate into math and vectors? Let's dive into the mechanism.
Okay, the intuition feels solid. Now for the how. Show me the query, key, and value vectors and how they make this happen.
The core of self-attention starts with creating 3 vectors for each word: a query vector, a key vector, and a value vector. Think of these as different aspects of a word.
Query, key, value, like a database lookup. The query asks for something, the keys match it, and the values are what you retrieve.
That's a good analogy, and it's exact in this case. These Q, K, V vectors are created by multiplying the embedding by 3 matrices that we trained during the training process. These matrices learn what features are important for querying, matching, and passing information.
So, for each word, its embedding is transformed into 3 different representations, and these transformations, the matrices, are what the model learns.
The next step is to calculate a score. The score is calculated by taking the dot product of the query vector with the key vector. This measures how relevant each word is to the current word we're processing.
So if I'm processing it, its query vector is dot producted with the key vector of animal, and then with street, and so on.
The higher the dot product, the more semantically related they are?
Exactly. For a word at position 1, Q1, the scores are the dot product of Q1 and K1, then Q1 and K2, and so forth for all other keys in the sentence. This gives us raw attention scores.
This confirms the database lookup analogy. The query of it is scanning all the keys in the sentence to see which ones are the best matches. Fascinating.
After dividing the scores by the square root of the key vector's dimension, dk, to stabilize gradients, we pass the result through a softmax operation. Softmax normalizes the scores so they're all positive and add up to 1. These are our attention weights.
So these normalized scores tell us the exact proportion of attention to give to each word in the input sequence for the current word. It's a distribution of focus.
The final step is to multiply each value vector by the softmax score. The intuition is to amplify the value vectors of relevant words and diminish irrelevant ones.
This is where the value part of QKV comes in. The query and keys determined how much attention, and now the values are what information gets passed along, weighted by that attention.
Finally, we sum up the weighted value vectors. This produces the output of the self-attention layer for that specific word. This new vector is a rich, context-aware representation of the word.
So the output for each word is a blend of all the other words' values weighted by their learned relevance. This gives us a new representation enriched with context from the entire sequence.
This description covers a single attention head, but the transformer actually uses multi-head attention, allows the model to jointly attend to information from different representation subspaces at different positions. It runs this process multiple times in parallel.
So instead of just one way of paying attention, the model learns several different ways simultaneously, like having multiple perspectives on the same sentence?
Precisely. Each head can focus on different types of relationships. Say, one head looks for grammatical dependencies, another for semantic links. The original paper notes that the Q, K, V vectors within each head are often made smaller. They don't have to be smaller. This is an architecture choice to make the computation of multi-headed attention mostly constant. The results from all these heads are then concatenated and linearly transformed.
That's brilliant. It's like having a team of specialized attention mechanisms, each contributing a piece to the overall understanding of the word's context. This definitely adds to the model's power.
We've delved into the heart of the transformer's self-attention mechanism, from the high-level intuition to the QKV vectors and multi-head processing. But the transformer's influence extends far beyond language. It's revolutionizing other domains too.
Like what? We started with text, so how does this attention is all you need idea translate to something completely different, like images?
That's exactly what the Vision Transformer VIT set out to do. The key insight, building on the transformer's sequential nature, is that it treats an image as a sequence of image patches. Just like words form a sentence, image patches form an image.
So an image isn't processed pixel by pixel or through convolutional filters, but by chopping it up into little squares? And each square is like a word?
Precisely. The image is split into a fixed-size grid of non-overlapping patches, and each patch is then flattened into a 1D vector. This converts the 2D image data into a sequence of vectors, directly mimicking the token embeddings used in NLP transformers.
Okay, that's clever. Take an image, make it look like a sentence. But what about the order? Are you still using positional encodings?
Absolutely. Just like with words, the spatial relationship of these patches matters. So, learnable position embeddings are added to these patch embeddings to retain positional information. Without them, the model wouldn't know if a patch was from the top left or bottom right.
Makes sense. An object in the top left corner needs to be identified as being there, not somewhere else. What about classification? How does it tell if it's a cat or a dog?
For classification, an ingenious trick is used. To perform classification, a learnable class token, CLS, is prepended to the sequence of embedded patches. This extra token acts as a placeholder that, through self-attention, aggregates information from all the image patches. The final output of this token is then used for the classification task.
So this class token essentially becomes the model's summary of the entire image, allowing it to make a prediction? That's really elegant.
Exactly. The resulting sequence of embedded patches in the class token is then fed into a standard transformer encoder. No new complex architecture needed for vision. The core transformer mechanisms simply adapt to a new data format.
That really reinforces the core insight. Attention is all you need. Just reshape your data to fit the transformer and it can learn anything.
It's incredibly powerful, but it's important to acknowledge its limitations. One of the main challenges is its quadratic computational complexity with respect to the input sequence length. As the sequence, or number of image patches, gets longer, the computational cost grows very, very quickly.
So super high-resolution images or extremely long texts could make the model impractical to train? That's a significant bottleneck for real-world applications.
Another point, especially when moving to new domains like vision, is that while transformers are powerful, with smaller data sets, the lack of inductive biases means they do not generalize as well as CNNs. CNNs inherently understand spatial relationships, but transformers have to learn them from scratch, requiring more data.
So they're data hungry. That means getting those groundbreaking results often requires massive data sets, which aren't always available, or comes with huge pre-training costs.
Absolutely. The transformer has redefined what's possible, from generating human-like text to understanding complex images. It's a testament to the power of a simple yet profoundly effective architectural shift, even with its inherent challenges.
From a bold claim in 2017 to truly reinventing AI across modalities, the Transformers journey is fascinating. It really does feel like attention was all we needed to unlock a new era of deep learning.